Oh, wow, it's 9:02. All right. Okay. Hopefully. All right. So, welcome back. Today we're going to be talking about linear transformations, and I think 4.8 through 6.1. Let's see. We don't need this, and we don't need that. Let's erase that as well. So I think the big thing we're going to be really dealing with is we're going to be looking at this guy on the board, ax equals b. So let's just write that in. Ax equals b. And we really care then about just the dimensions of ax equals b. So a is going to be m by n, and then x will just be our column vector n by 1, and then b then is supposed to be m by 1 by just the multiplication of matrices. So today we're just going to start off talking about linear transformations. And the whole idea then is that ax equals b, this is a linear transformation. So a is actually a linear transformation. And what is it? Well, a is a map between Rn and Rm, okay, where ax is equal to b. So what does any of this mean? Well, so A is just the name of our map. All right, and then we have Rn is the input vector space, and Rm is the output vector space. Okay, and this makes sense in the context of this picture on the board, because so A eats a vector in Rn and then spits out a vector in Rm. So that's what all that on the board is talking about. All right, so we know it's a linear transformation, but what specifically then is a linear transformation? Well, the definition is the following. The definition of linear transformation is, so a map T from V to W is a linear transformation if it satisfies the following properties. Okay, and there are two of them. So the first one is, all right, let U and V be inside our input vector space, which is the big V. And then we will say T of U plus V is equal to T of U plus T of V. And the second property then is, okay, so now let K be a scalar. Actually, okay, doesn't matter. Then you want T of K U is equal to K times T of U. All right, so if it satisfies these two properties, then we know we have a linear transformation. And yeah, so matrix multiplication up there, it's almost like immediately clear that it satisfies these properties, right? Because if you choose any two x's, well, it's distributive, so that's satisfied. And then if you let x be some constant times a vector, you can just pull the vector, the constant out in front, so that works as well. So that's why matrix multiplication then is a linear transformation immediately. But let's take a look at some other examples. And how do we show this formally? So this first example, then, let T be a map from C2I to C0I. And you can think of C2I as continuously twice differentiable. and then we take two derivatives off of it. So what do we do? Well, t takes an input y, and it splits it to y double prime plus y. Okay, so that's our map. And we want to show that it's a linear transformation. So what do we have to do? We have our two conditions, right? We have essentially closure under addition and closure under scalar multiplication. So this looks a lot like what we did for vector spaces and subspaces, right? So what we have to do then is, okay, here's plus. So we have to show it's closed under addition. And we need to choose two arbitrary elements in our input vector space. Okay, so does anyone have two arbitrary elements they want to give me in the input? Not quite. What does my input look like? Or at least given my map, like what are my inputs? Sorry? They're functions, right? They're continuously twice differentiable functions. So they could be polynomials. But what I'm looking for is, all right, so on my second line, that tells me explicitly what my map is, right? It takes y and it sends it to y double prime plus y. So an arbitrary input into my function would just be like y1, right? Or it'll be like y17, right? So what I want to do then is I want to take, let's say, y1 and y2 inside of C2i. So that's what I mean by taking two arbitrary elements, right? You know your inputs are ty's, or just y's. So now we have y1, y2. These are my two arbitrary elements in my input vector space. And so now we got to apply t of y1 plus y2. So what is this equal to? Well, okay, so t of y was y double prime plus y. So now everywhere we have a y, we just replace it with y1 plus y2. So we get y1 plus y2 double prime plus y1 plus y2. We can distribute this double prime. So plus y1 double prime plus y2 double prime plus y1 plus y2. And then let's just match terms. So let's add have the y1s be aligned next to each other, have the y2s be aligned next to each other. Okay, but what is what is y1 double prime plus y1? Yeah, exactly. It's t of y1. And then what is y2 double prime plus y2? Yeah, t of y2. And so we've done exactly what we wanted to do up here, right? We split up this u plus v into a u plus a v. And so we have t of y1 plus y2 is equal to this. So that's good. All right, scalar mult. So choose a scalar k, arbitrary input. So what we're going to do is we're going to take k and r, and let's just take y and C2i. So now what do we want to do? We want to take t of ky. And what is that? Well, we just replace the y's with ky. So now I got ky double prime plus ky. Which is, I mean, I can just factor out that k in front. So now this is ky double prime plus y. And what is y double prime plus y? T of y. And I forgot the k out in front, but there you go. Kt of y, which is exactly what we have for the second case. So that's good. And therefore, this is a linear transformation. Any questions? Okay, so it's fairly straightforward. It's a lot like doing the vector space stuff. Let's see another one. So this was number 1. And this is number 2. Okay, so let's take P, and we're going to go from P2R into M2R. And what is the map? Well, it takes ax squared plus bx plus c, and it feeds that into this matrix A, B, C, 0. Okay, so under plus. So what do you do under plus? We choose 2 arbitrary elements in the input vector space. So what are 2 arbitrary elements in my input vector space going to be? Yeah.
Like 2 quadratic functions?
Yeah, so 2 quadratics, but we kind of have to specify them here. So we can't just be like y, because if you look at my input, right, they're like written out. So, okay, so let's call them a1x squared plus b1x plus c1. And then I'll choose a2x squared plus b2x plus c2. And we're going to take these in P2R. Okay, and then now we got to do T of these 2 polynomials added to each other. So this is really a1 plus a2 parentheses x squared plus b1 plus b2 parentheses x plus the quantity c1 plus c2. And what is this equal to? Yeah. So I just take the coefficient in front of my whatever term and put it appropriately. So a1 plus a2 is in front of my x squared term, so that goes up here. a1 plus a2. And then my b term, right, the term in front of the x goes in the top right, so this becomes b1 plus b2. Then I got c1 plus c2, and I get a 0 on the bottom. Okay, what is this equal to? This is equal to a1, b1, c1, 0, plus a2, b2, c2, 0. But what is a1, b1, c1, 0? Yeah, T of the first polynomial, a1 x squared plus b1 x plus c1, and then a2, b2, c2 would be T of the second guy, a2x squared plus b2x plus c2. Okay, so that's closed under addition. Now let's do scalar mult. So now we'll just take k and r and ax squared plus bx plus c in P2R, and we get t of, all right, so we got to do t of k times this polynomial, which is really then each of the coefficients just gets multiplied by k. So kbx plus kc. And then now we toss it in our matrix. All right, what is our matrix? Ka, kb, kc, 0. All right, might as well factor out a k. And we see that now we have k times abc0, which is just t of ax squared plus bx plus c. And so this is also linear transformation. And then now, any questions on this one? All right, so one last example. And this is what happens when something is not a linear transformation. Right? So the first two examples were linear transformations. And when you have a linear transformation, right, it's kind of like a subspace. You have to show both conditions hold, right? But when something, if you have a hunch that it's not going to be a linear transformation, you only need to find one counterexample. All right? And so for subspaces, it was usually the 0 vector. But here, right, we can just find a counterexample. So let's say we have this map from M2R to R. So we have a matrix. We put in our map, and what does it do? Well, it takes the determinant of the matrix. So why is the determinant of a matrix not a linear transformation? So we need to find a counterexample. Can anyone think of one real quick? So either one has to fail, closure under addition or scalar multiplication.
Closure under addition for identity.
Okay, so yeah, so that one works. So yeah, why don't we do that one then? So let A equal 1, 1, and B also be 1, 1. Right? Nothing's stopping us. Well, T of A plus B is equal to T of 2, 2, right? Because A plus B, you're adding the two identity matrices together, and then you're getting 2, 2 on the diagonal now. But what is that? This is the determinant of 2, 2, which is 4. But what is T of A plus T of B? Well, that's equal to the determinant of A plus the determinant of B, which is equal to 1 plus 1, which is 2. All right, and then we see that these two then are not equal to each other. So it's not closed under plus. Any questions? So we're done here. So this one also fails under scalar multiplication. I mean, you can go home and play around with it, but the determinant is most certainly not a linear transformation. All right. Yeah.
Is there a case when it's like really difficult to find an example unless you like have some sort of is there like a method?
Yeah, so usually you want to play around with like the simplest thing. So like here we just jumped straight to like the identity matrix. Yeah, so usually you want to play with like zeros or like identities or just like really simple, because usually what happens is that the counterexample is going to be something really simple. Yeah, so you don't have to come up with like an elaborate counterexample. Any other questions? All right, so those are linear transformations. There are a bunch of these on your homework, so now you know how to do them. Let's go to, so let's revisit then this whole idea of the matrix being a linear matrix multiplication being a linear transformation. So we're going to talk about column space, which is 4-8, I think. It also includes row space. Linear transformations is chapter 6. It's 6-1. So column space is 4-8. We're kind of going backwards. So we have A times X equals B. So A is actually a linear transformation. And sometimes we want to ask ourselves then, what like possible values can A hit? Right, so if we're thinking A as a map, right, A is taking in something from Rn, and we're going to Rm. So in other words, right, what is the image, or you guys might be more familiar with range of A? Another way we can phrase this problem is, what does B have to be such that AX equals B has a solution? All right, so these are all equivalent questions, right? What values of B can A hit? Or what values of B makes it such that AX equals B has a solution for some X? So those are equivalent questions. And the answer to all these really lies in, we want to look at the column space. With A, which brings me to the definition of column space. Which is the following. It's pretty simple. It's the span of the columns of A. Okay, so for example, let's jump into an example to see what this means. Let's find the column space of A is equal to 1, 4, 7, 2, 5, 8, 3, 6, 9. Okay, so how do we find the column space? Well, we take this matrix, 4, 7, 2, 5, 8, 3, 6, 9, and we want to row reduce it so we see our pivots. Okay, so we're just going to do some standard row reducing, zero out that first column, and this becomes -3, -6, -6, -12. All right, and then since the only thing we really care about is putting this in, like exposing our pivots, we can just zero out that last row. I'm going to say, okay, that's fine. So what do we have now? We have pivot, pivot, free, right? Here's a pivot, here's a pivot. And so what is my column space? Well, the pivots give me an index of which columns span. So since this first column is a pivot, I know the first column of A is going to span. So I go back to A, and okay, so that is going to be in my column space. And then the second pivot is in column 2, so I go back, and I'm going to take that in my column space as well. And we're going to see that the column space of A is equal to the span of 1, 2, 3, and then, whoops, 4, 5, 6. So just as a quick refresher, right? What does it mean for this, like, for a column space to be the span of these two vectors? Yeah, so it's all linear combinations of these two vectors, right? So that's going to be like, I don't know, C1 times 1, 2, 3 plus C2 times 4, 5, 6. Right? It's literally, and then you can pick any C1 and C2. So that's what the span of that set of vectors means. So the column space is everything that's a linear combination of those two vectors. And we can kind of see it, right? We can kind of see it. I mean, if you take this matrix up here, right? We take our original matrix, and let's say we do the following. Let's say I call this first column, let's say I call this V1. I call the second column V2. I call this third column V3. All right. So remember that the column space is all values B can be such that AX equals B has a solution. So if we rewrite A as V1, V2, V3, right? So I essentially just took each column and I collapsed it down into like this vector notation right here. Right, I took 1, 2, 3, that's V1, 4, 5, 6, that's V2, 7, 8, 9, that's V3. And we multiply it, right, by the unknown x vector. So now this is A, this is x. So what dimension does x have to be? It has to be 3 by 1, right? Because I have a 3 by 3 square matrix. So this would be x1, x2, x3. And all right, so we know B is equal to this. I'm going to put it on the left-hand side, right? It doesn't matter. So B is equal to AX. It's the same thing as AX equal to B. So we got B is equal to this stuff. And if we multiply it out, if we multiply this stuff out, what do I get? I get x1 v1 plus x2 v2 plus x3 v3 right? So we can see that. All right, so what are x1, x2s, and x3s? Like what type of, like are they a vector, a matrix, a scalar? They're all scalars, right? x1, x2, x3, because they're inside the vector. So really, you can really think of this as, this really looks like C1 v1 plus C2v2 plus C3v3, right? Because they're all just constants. They're all just scalars. And now we can see, hey, look, this is really C1 times 1, 2, 3 plus C2 times 4, 5, 6 plus C3 times 7, 8, 9. Because that's what I called V1, V2, V3. So now what do we have? Now we have B is equal to this linear combination, but that's just, that linear combination is essentially what we just solved for in our column space up there. Right? And what does this tell me? This really pretty much tells me that 7, 8, 9 is a linear combination of 1, 2, 3, 4, 5, 6, but it's fine if we leave it in there anyways, because it's just going to be some redundancy. But this is how we can see that B has to lie in the column space of our matrix. Does that make sense? Does it make sense what I did here? We're just showing why B has to lie in the column space. That's why. Okay. What's the dimension of the call space of A? Yeah, it's 2, right? Because I have 2 vectors in here. So the dimension is equal to 2. And what is the rank of A? Yeah, it's also 2, right? Because I have 2 pivots. So that's it's an important observation to keep in mind that the dimension of the call space of A is going to be equal to the rank of A, which is equal to 2. Which is equal to, well, in our case it was 2, but the more important thing is to remember the dimension of the column space is equal to the rank. All right, any questions? That's pretty much it for column space. I just wanted to show that B lies in the column space of A. Okay, so let's move on. It's the Rank-Nullity theorem, which is 4, 9. And we're going to talk about the column space just a little bit here because it's relevant. Okay, so what does the column space deal with in terms of this equation right here? In terms of AX equals B, like what parts of this are we concerned with when we talk about column space?
Set of all solutions. What the span of all the solutions of which the points be.
Is the span of the solutions?
So our span of the 2 vectors of the column space is the set of all solutions.
It's not the set of all solutions, right? Because the solutions talk about X, but did we really talk about X up here at all? No, like not really, right? I even called X like a different name.
Set of all B's, sorry.
Yeah, yeah. So the column space is really like the set of all B's where this has a solution, right? So the column space really don't care about like the B's, right? We care about the A, right? Because that's how we find our column space, but we also care about the B's, right? So column space deals with the B's. And what's the, where is, so since the column space deals with the B's, what is the column space a subspace of? In terms of this m by n crap.
Um,
Is it the span of B?
Well, yeah. Well, technically, yeah, the call space of A is also like the span of B, but or it forms a basis that spans B. But I'm talking about like in terms of subspace, like. So you have two. You really have two answers. It's either an Rm, or it's an Rn. Okay. So where would the call space lie? Rm, right? Because we were talking about the span of column vectors, right? And so column vectors are m by 1, right? So the column space has to lie in Rm. Another way you can look at it is, hey, look, we only care about B's, which are m by 1. So the call space is a subspace of Rm because we really only care about the B's. What's another subspace of like this equation that we like learned about? It was actually on your midterm. Yeah, the null space, right? So the null space is another space we care about. The null space deals with which element of this ax equals b equation? Right, so b gets forced to be 0, right? So we don't really care about what b is. We care about what the solutions to ax equals 0 are. Right? So in that case, we care about the x's. And the null space of A is in what subspace? It's a subspace of what bigger vector space? Rn. Right? And that's because, look, we care about the x's, and the x's are n by 1. Okay, so what does this even deal with? Well, we kind of have to tie these together somehow, right? But the column space is like a subspace of a completely different, bigger vector space than the null space is. But the Rank-Nullity theorem actually ties this all together. And it says the following. The Rank-Nullity theorem tells us that the dimension of the column space of A plus the dimension of the null space of A is equal to the number of rows, number of columns. Columns. Notice we're not even talking about rows today. So columns. All right. And so what does this mean? Well, what is actually the dimension of the column space? What is that equal to? Rank. So it's equal to the rank of A plus, and dimension of the null space, it's called the nullity. All right, and that's equal to n, right? Where n by n matrix, n is the number of columns. And so let's just say the definition of nullity, we're just going to write it in here, is the dimension of the null space. Okay. So the Rank-Nullity theorem ties together pretty much these two seemingly unrelated subspaces. So let's look at an example. We're going to look at an example of just showing that this thing holds. Okay. So let's take this matrix A is equal to 1, negative 1, 4, 3, 2, negative 2, 8, 1. Okay, so let's find the call space of A first. So we're going to reduce it, zero out the first column of the last row. It ends up zeroing out a bunch of stuff. Zero, 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 -5. Okay, and we see we have pivot, free, free, pivot. So what is the column space of A?
The span of the first and fourth column.
Yeah, the span of the first and the fourth columns, which are 1, 2, and 3, 1. And what's the dimension? 2. Because there are 2 vectors there. All right, and now the null space of A. So this one's a little more involved because we have to like find the solution to this equation. So really think of it as like an augmented equation with some zeros on the end. Okay, so we know that x4 is equal to 0 because that's what the last row tells me. And then the first row tells me that x1 minus x2 plus 4x3 plus 3x4 is equal to 0. But we have some free variables, namely x2 and x3. And so let's say x3 is equal to t, x2 is equal to s. Then x1 has to be equal to s minus 4t. By solving that equation from row 1. Okay, so this gives me then x is equal to the following: s minus 4t, st 0. But we don't really want to write it like this because we can't really, like, this doesn't tell me what, like, the basis vectors of my null space are. So what we're going to do is we're going to extract them, and we're going to say, okay, this is equal to s times 1, 1, 0, 0, right? Because I have the s's here, so then it's s times 1, 1, 0, 0. And then I'm going to add t times, all right, and where are the t's? The t's are there and there. So this becomes -4, 0, 1, 0. And, ooh, whoa. And so really we want to say that the null space is equal to the span of 1, 1, 0, 0, -4, 0, 1, 0. Is everyone okay with that? All right, and then what are my dimensions of my null space? Yeah, the dimension is equal to 2. So then we got 2 plus 2 is equal to 4 is equal to the number of columns. Okay, any questions? All right, one last thing. So let's talk about the general solution to a system of equations. So when we have ax equals b, again, we're dealing with this guy again, we can write x is equal to xp plus xh, where xh is the solution to the homogeneous system, and xp is a particular solution. So what is xp? Well, xp literally just means anything that satisfies ax equals b. And homogeneous system is ax equals 0. All right. So x can be written as the sum of these two. And why do we even care about writing it this way? Well, it's because when you solve differential equations, you kind of have to do it this way. All right, so we're just prepping you guys for that part of the course. And also, I guess it's like kind of an application of the Rank-Nullity theorem, but whatever. So, for example, let's take this matrix 2, 3, 1, or the system of equations. So 2, 3, 1, big augmented line, and then 6. And let's do -4, -6, -2, -12. All right, so we want to find the solutions to the system. So xh is the homogeneous system. So we kind of just rewrite the right-hand side to be zeros. All right, reduce. So we get row zeros on the bottom, and now we just want to find what this is. So this is really finding what the null space is, right? So I guess another way to look at this first part is xh is the null space. But anyways, so okay, so now we got to solve this. What do we got? X3 is equal to t, x2 is equal to s, x1, 2x1 plus 3x2 plus x3 is equal to 0 from row 1. And then solving for x1, I see this is equal to -3/2 s minus 1/2 t. So xh is equal to -3/2 s minus 1/2 t s t. All right, so what is the particular solution? Well, the particular solution, any issues with the homogeneous? Really shouldn't be, because we've been doing this for forever now. Okay. Particular solution. So now we go back to the entire thing. And all right, I'm going to take a row. I'm going to row reduce one of these. So we're going to kill out this last row. All right, because any solution to this guy will just be a solution to that, since row reduction doesn't change our solutions, right? So, all right, so what is a particular solution? Particular solution just literally means anything that makes this true. All right, so I can literally pick anything. So there are an infinite number of these that are correct. So what are some possible XPs? Anyone? Literally anything that makes this true. 1, 1, 1. All right, anything else? 3, 0, 0. We're going to keep going until you guys pick the one ahead. 0, 2, 0.
0, 0, 6.
Yeah, 0, 0, 6. Okay, that's the one ahead. All right. So do you guys understand how we choose these particular solutions? We just literally look at that system and we just pick whatever one. So you can take any one you want from here. They're all correct. We're just going to take this one because that's the one I have on my sheet. And so now x is equal to xp plus xh, which is really equal to, all right, so xh was this null space stuff up here, -3/2 s minus 1/2 t s. And then since I picked 0, 0, 6, this becomes t plus 6 on the bottom. Any questions? All right, that should be enough for you guys to do your homework this week. It's kind of long, so I'd recommend just taking a look at it today or tomorrow, just to get a few problems out of the way. It's like 15 or 16 problems, I think. So yeah, so next week, Davi didn't get as far in class as I thought he would yesterday, so I think we're going to be still on linear transformation. I might introduce eigenvalues before him if he still goes really slow. Actually, you guys are on Friday, so he'll probably have done it by Thursday then. So, all right. Yeah, so reminder, I have office hours today and Monday if you have any questions on the homework, and I'll see you guys next week. And this is also recorded, so it's going to be put up on the website by this afternoon. And midterms if you haven't picked yours up yet. Yeah.
In relationship to so x is equal to what does x represent? Is it straight x?
X is literally the solution to AX equals B.
So it's another xp.
So what's another XP?
No, is this vector x another?
No, X is this X is this X. I can just break up this X into an XP and an
In
XA.
terms of the null set of a vector, right?
Yeah.
So this is essentially the null space, correct?
Yes, XA is the null space, yeah.
So you're telling me that this is sort of a shift in relation to
Yeah, it is. That's I didn't get to the geometric interpretation, but that's exactly what it is. Name? Should be. Okay. I'll take someone's question. You want to ask me a question while I look?
Wait, yeah.
Yeah.
First, is homework 4 gonna get returned soon?
Oh yeah, I have it. It's just unsorted. If you want to dig through the file.
Sure. And then I guess why problem.
Yeah.
This is the last.
Right. Yeah.
So I understand to find. So have you seen? You're familiar with circle?
Yeah.
So for V, you need to just kind of like take 0 and see where that can translate.
Right.
But I don't really know how to find them.